What is the second derivative? So by now we're comfortable with finding the first derivative of a function. So let's do that now. The first function we have here is y equals x squared. The derivative of that we call y prime, and we know that's just equal to 2x. The second function here, y equals 3x squared, we can find the derivative of that as well. We would call that y prime as well equals, bring down that 2, so it's 6x. What about this third function? We can find the derivative of this as well. This one I'm going to use Leibniz notation just to change it up a bit, but it's really the same thing. So dy by dx is equal to, well, it's just 2. And this last one, y equals x cubed, actually I'm going to change this question a little. I'm just going to call it, instead of y, I'm going to call it f of x, just so we see what the different notation looks like. So the derivative of this we would call f prime of x, and that's just going to be 3x squared. Alright, that's what we know how to do. Now, what do these things actually represent? Recall how these are just the derivatives of these functions, which means it's the slope of the tangent at any point. So if we look at 2x, 2x is going to be a line that goes diagonally up, which tells us that the slope is going to constantly increase. And if we think about the slope on this line, that's going to sort of start off negative, and it's going to constantly increase. This one here, 3x squared, same thing. Starts off with a negative slope, and it's going to increase. It's going to increase at a faster rate than this one because it's sort of a steeper curve. This third one here is just a line. So the rate of change, or the slope of the tangent, never changes, just a constant of 2, which we know as the slope of this line. Lastly, we have this complicated curve, right? So the derivative is a quadratic. And that makes sense because a quadratic, we know, sort of is going to dip down like this. So it's going to be, it's going to be positive, and then it's going to go to 0 and then become positive again. And that's sort of what happens here. It's positive slope, gets less steep, and then goes back up. So we're comfortable with the first derivative. Well, we should call the first derivative. Now let's take the derivative of the derivative. Why would we do that? Well, we're going to find out. So I'm going to call the derivative of the derivative the second derivative, and that's the topic for today. And essentially, it's just the same thing, but instead of y prime, we have the awesome notation of just y double prime. So the derivative of 2x now is just going to be 2. So that's the second derivative of x squared. We can also show it here as y double prime is just going to be 6. This one here, we use different notation here. So how do we show the second derivative with this Leibniz notation here? Well, actually, the way we do that is we say it's d squared y with dx squared. And that's going to be, well, what's the derivative of 2? It's just 0. Again, this just means the second derivative. The reason why it's d squared y over dx squared is something I'll talk about a little bit later, but this just essentially means the second derivative, which is the same thing that these things mean. Over here, we can take the derivative, and it's going to be f double prime of x, and that just equals, well, bring that down, so 6x. Now, we know that the first derivative represents the slope of the graph at any point. What does the second derivative represent? Well, we can look at it. These two first quadratics both have a constant value for the second derivative. So what's constant about these two? We can ask the same question here for the third one, for the line. The second derivative is just 0. And for this fourth one here, the second derivative is not constant, it's not 0, it actually has a changing value. So the way I like to think about it, what's the difference? What do these functions have, these two functions have, that this one doesn't have? And really, the difference is curviness, right? This graph here has no curviness, so the second derivative is 0. These graphs here have some curviness, so that's why their derivatives, second derivatives are constant. This graph here has a lot of curviness. It's got curviness going this way, and then it's got curviness going this way, and that's why its curviness, the second derivative, is more complicated. And I'm calling it curviness, but really what the second derivative tells us is something called the concavity. Let me write that down. So it has to do with the concavity. of a function. Okay? These functions here both have positive concavities. And probably back in grade 9 or 10, you learned about, or grade 10, I guess, you learned about parabolas and how they're either concave up or concave down. Well, that's exactly what the second derivative tells us. It tells us if it's a concave up or concave down. So here, these two, we can see, are both positive, and that's because they're both concave up. So let me just write that in there. This is concave up. Okay, so both of these positive concavities, so they're concave up. This one here, it's not curved at all. It's not curved up or curved down, so it's got no concavity. And then lastly, this one here, this one's a little bit complicated because it sort of looks like it's a parabola on this side that's facing downwards. Like if we look at if we look at this half here, right, it just looks like a parabola that's going down. So this half here looks like it's concave down. If we cover up this side and look here, we see that this side, it looks like it's concave up. So that's what we say. This side is concave down, so it will be negative concavity, and this side is concave up, or positive concavity. Okay? One more thing. What about if we change this equation here? What if I write a second equation? Instead of y equals x squared, what if I put the second equation, and get a marker out, of y equals negative x squared? Well, we know this function looks like this. So what's going to be the concavity of that function, do you think? Positive or negative? Think about it. And then we can check by actually taking the second derivative. So y prime in this case is just going to be negative 2x, and then y double prime is going to be just negative 2. So see, we have this is actually going to be concave down, which makes sense because it's a downward facing parabola. Okay? All right. So let's go to another example. Here we have two problems, or two things we're asked to do for this same function. I just drew the function twice. The first one, we're asked to find the positive and negative slope, where the function has a positive and negative slope. And the second one asks us to identify where there's positive and negative concavity. So let's start off with this first one. We know how to do that. That's based on the first derivative of the function. Okay? So I'm going to call everything that has a positive slope, where on the graph has a positive slope, I'm going to say that that is a positive slope in red. Oops, I can't spell positive slope. Or another way of putting that, we would say the graph is increasing. So where on this graph is it increasing? Let's start here. Are we increasing? Does it have a positive slope? Yeah, it does. Where does that positive slope stop? Well, it stops where we have this point up here. So it's going to continue all the way up to there. And then if we look, we have a negative slope, negative tangent. The graph is decreasing, decreasing, decreasing. Stops decreasing there, but then just continues decreasing all the way down here. Rolls downhill until sort of this point here, at which point the graph starts increasing again, right? So we have these two regions where the graph is increasing. And it looks like from here, so we'll put the blue will be negative slope. And this is where the graph is decreasing. Right? And we see that's sort of in this whole region here and continuing down there. The graph is decreasing for that whole piece. Okay? Also, between these 2 points where it changes, what do we call those points? This here, oops, let me get a better marker there. This point here, we call a maximum, more specifically a local maximum. And this point here, we find a local minimum. Okay, so we're comfortable with that. What's special about the tangent at these 2 points? We should remember that at these 2 points, the tangent is horizontal. So the derivative at these points is equal to 0. The derivative here is going to be positive. The derivative here is going to be negative. That's what the negative slope is. And then here again, the derivative is positive. So now let's do the same thing except for the second derivative, or the concavity of the graph. Where is the graph concave up? Where is the graph concave down? And what's in between? So, in red, we're going to do positive concavity. And another way of putting this is concave up. So basically like an upwards opening parabola. So where on this graph does it look like an upwards facing parabola? Well, the obvious one is over here, right? It looks like a parabola facing up. So this does have positive concavity. Now, where does that finish? Where does that stop and turn into a negative concavity? If we sort of cover up here, we can sort of see, we reveal the parabola a bit at a time. Where does that stop? Well, sort of here. Do you see how it starts to curve downwards? So there's like a point in between where it starts, see here it still looks like a parabola, so let's continue like that. So maybe a point like that where that parabola ends, right? Another thing right here, it looks like it's a parabola. Oh, that looks like a parabola down. But here, if we just look at this region here, that sort of looks like an upwards facing parabola too. Now it doesn't continue like this, but it sort of looks like that. So we would say that this region here, something like that, also has a positive concavity. Okay, even though it's sort of just part of a parabola, it still looks like it's opening upwards. Okay? If we look at the other parts, specifically where there is a negative concavity, this is where we have a, or we can also call this concave down. Okay, so it looks like a downward facing parabola. Well, the obvious place is this part here looks like a downward facing parabola, right? So this whole part, until it sort of starts to sweep back up, so that looks like it's concave down. And if we just look at this little part of the graph here, this little green part here, it looks like a downwards facing parabola, right? So there, we've identified the regions of negative concavity and positive concavity. So, remember what that means. The second derivative for this region is going to be negative, and for this region it's going to be negative. The second derivative for this region and this region are going to be positive. Okay? Now the question is, what are these points in between where they change from having a positive concavity to a negative concavity? We actually have a special name for those. If I can find my other marker. Oh, here it is. We call these points points of inflection. Okay, so there's one of them there where it switches from a positive concavity to a negative concavity. There's one of them there as well, and there's also one of them right there. So we would have 3 points of inflection along this graph. Now the thing to remember, if we go back up to this graph, how can we identify where the maximum and minimums are? Well, that happens where the slope of the tangent is equal to 0, right? So this happens where f prime of x is equal to 0. And the local maximum also is where f prime of x is equal to 0. So where do you think these points of inflection are going to occur? Well, just sort of carrying on what that said, it's where the second derivative is equal to 0. So if we just find the second derivative, we take the second derivative of a function, set that to 0, and solve for x, we can find where these points are. That becomes very handy when we're trying to sketch the graph of a complicated polynomial or other sort of function. And it also has some applications in physics, which we're going to get to in the course.